recording for everyone who's not here. Or if you guys want to hold me to something, now's your chance. All right. Oh yeah. So I wanted to show you on Moodle because, so what I want to do today is not this. I want it to stop doing this. Is to finish ANOVAs. Just kind of a quick review. What do we do if we find that the ANOVA is significant, right? That means that there's something going on with these means. So then what do we do? And then what I want to do is I want to go through, I have all these practice questions. We're going to go through about half of them and just talk about why they are the types of questions that they are. And then I'll leave the rest for you to work through. I'll post the solutions so that you'll have them, as well as the worked through numerical answers, which you can do for practice. It uses the tables because they're slightly outdated, but you should get kind of similar answers. Okay. I also posted this RMD file mostly, oh, okay. So maybe I did not. I didn't, doesn't want to do it. Here I am as a student. Will it open? There. RMD files, I find that they kind of post weird on Moodle, so you'll have to copy paste it over into a new RMD file. But the only reason I'm giving you this is so that you can see how to generate this type of answer, right? So I'm kind of showing you a little bit more of what you can do. For example, you can reference the p-value itself. You don't have to hard code it, right? Because then if you rerun your analysis, then it'll be reproducible, right? And then that kind of thing. But that's just there if you want it. Okay. Oops. How to write your hypotheses in LaTeX, for example, that kind of fun stuff. But that's just for fun.
Can we get into more of those types of questions in future classes, stats classes?
Yeah. Yeah. Like in 240, we're going to work through a bunch of code. Yeah. So you'll have a jumping off point, and then we'll just kind of like dissect it, which would be similar to this, right? I kind of give you something and then you kind of plod through it. Wait. Just to make a note. Maybe we don't need last week's stuff. This is just for fun. Okay, that looks like a mean smiley face. Fix that. Whee! There. That's a nice smiley face. All right, so that one's just for fun. I'll post the PDF as well, but I just wanted to show you that the RMD is there. Okay, in terms of review, just to review ANOVA in general, right? What we said was the conditions aren't that complicated. We added that new condition of we have to have constant variance or roughly constant variance across the groups, which would typically, we would use a side-by-side box plot, right? If they have roughly the same width, then we're satisfied, meaning that the standard deviations should be roughly the same. But for us, right, we will assume conditions are met or are satisfied, let's say, right, for our purposes. in an ANOVA, the null hypothesis, and maybe I should label it step 1, right? And this is a review from last day. So step 1, state the hypotheses. How we are talking about the ANOVA is for means, right? So now I have more than 2 means. If I have 2 means, I should just do a 2-sample t-test if I want to compare the two, right? But if I have more than 2 means, so 3 or more, then my null hypothesis is that mu1 is equal to mu2. Wait, that doesn't look like a 2. Is equal to all the way equal to mu k, where k is the number of groups. All right, so we use it to compare k groups. Same setup as before, right? In words, all the means are the same. We don't mean same, we mean statistically not significantly, or sorry, yeah, significantly different from each other, right? Same. The alternative hypothesis, then, it doesn't tell us which mean is different, and that's what we're gonna just kind of briefly tackle today, but it does tell us that there is one mu I that's not equal to mu j, where I can't be j, right? I have to be talking about 2 different groups. Okay. That's the notation that we would use. In words, we would say at least one mean is significantly different from at least one other mean. At least one mean is significantly different from at least one other mean, from at least one other mean.
Do we need that where I is not equal to j part?
It's assumed, but because you're using 2 different things, but I mean, if you just let I and j be integers, then you could let I be 1 and j be 1. So that's why you want to, and you don't want to say mu1 is not equal to mu1, right? It's implied, but just math, right? Being proper. Okay, so step 2 that we do the test. That's going to be given in software output. And it's the F test statistic is the test that we're running, right? And we talked about the anatomy of that ANOVA output, right? And I do expect you to be able to fill in the blanks just like you do on the assignment, right? So kind of knowing the anatomy of it, not necessarily calculating any of those sums of squares or anything that's crazy. Step 3, find the p-value for an ANOVA, right? Usually it's given in the software output. If it's not, right, if you have an F test statistic, you can use that probability calculator, right? So it's either given in software output or use the probability calculator with DF1, and that's kind of a generic way to write it, but it translates to the calculator as well, is the number of groups minus 1, and DF2 is n minus k, notice when you add these up, so the total degrees of freedom is still going to be n-1. But these are given in the software output. Typically. So you'll have the p-value somehow, right? Or you'll have to find it in the probability calculator. Step 4 is the conclusion, which is the same as always. I know, I never tell you what it is. What is same as always? If the p-value is less than the alpha level, we have enough evidence to reject H0 in favor of HA. And then what does that mean in terms of the question? Continuing from the conclusion last day, and maybe this is the end of our review here. Keep it on the same page. Or better yet, bump this out up just not like that. One line. Can I do it? There. Sneaky. There. Continuing the example from last day. I'll snag it. All right, we can run through. So in this output, we were given the p-value, but then I also showed you how to use the calculator with the F distribution, degrees of freedom 1, degrees of freedom 2. You don't want to mix those up, right? It's important that you do them in the right order. For the F distribution, it's always the area in the upper tail, right? Same thing as the chi-squared. As soon as it's skewed, then you use the upper tail. And then we found the p-value that way, right? So then we said, okay, since the p-value, and I think we, oops, copy. We finished it. I'm gonna change the color there. So we said, since the p-value of 0.0066 is less than the alpha level of 0.05, we have enough evidence to reject H0 in favor of HA, which means that the mean on base percentage, which is what we were measuring, of at least one of the positions, we were talking about 3 positions, is significantly different from at least one of the other positions, right? Could be one, could be both, whatever. Right. So now what? So if we find that our ANOVA is significant, right? And that's a term that we use. If it's significant, it means we've rejected H0, right? So if we find that our ANOVA is significant, right, we usually want to know, okay, well, which positions, right? Okay, that's fine, but which ones? So if we find our ANOVA is significant, which is really just another way of saying reject H0, or rejected, I guess. Right. By saying it's significant. So if we find our ANOVA is significant, which means we rejected H0, which we did, we usually want to do some what's called post hoc tests. So now, kind of after the fact, then we say, okay, I know something's going on, but what? Okay. So if we find our ANOVA is significant, we usually will want to conduct a post hoc test, kind of after the fact, I think is the Latin post hoc. I think it's after the fact, but I'm not. I'm willing to go with it. Yeah, come on. So post, I'm feeling pretty confident. Post hoc. Is it? I'm waiting for the verdict. Anyways, let's call it after the fact. Yeah, how's your Latin? I learned a new Latin one just the other day. Someone had written NB, nota bene, mark well. It's like an exclamation. Anyways, so if we find that our ANOVA is significant, right, we usually want to conduct a post hoc test to determine which group, and I'll put groups in brackets, are different from each other, or which I guess I should say means, although it does, which means are different from the others. Is/are different from the others. Oh, that's not a question mark. There are lots of different tests that we can run, many more sophisticated than what we're about to do, but I don't want to introduce another test. And so I'm going to take us back to the 2-sample t-test. We can do that, right? But I did warn you, right? You don't want to just run those 2-sample t-tests and use the same alpha level, because every time you do that pairwise comparison, you're introducing that type 1 error rate every time, right? And that's going to add up. So we just make a small adjustment. This is like the most basic form of post hoc testing that we can do. And so let's make a note here. There are many post hoc tests we can run. Oops, run. But we will focus on the simplest, which is the just using the 2-sample t-test, which we already know. But we will focus on using the 2-sample t-test. Oh, I don't know why I hyphenated. 2-sample t-test, which we already know. I want to say many things at once. I'll put which we already know in brackets, right? Using the 2-sample t-test to do pairwise comparisons. Okay, so there are many post hoc tests we can run, but we will focus on using the 2-sample t-test, which we already know to do pairwise comparisons. Okay, there are 2 adjustments that we make in your t calculation. We use a pooled standard deviation, and the reason I'm glossing over it so quickly is because I realize it's not on your assignment, which means it's not on your quiz, which means it's not on your final. So it's really just, here's something you need to know, right? If you were going to do this. Okay. So here we use a pooled standard deviation. To calculate the standard error. Which is also kind of contributing to why it's important that you have constant variances across the groups. but that's me going overboard. And then we adjust the alpha level and divide it by however many comparisons that we're making. So you adjust the alpha level by dividing it by the number of pairwise comparisons you want to make. By the number of pairwise comparisons you want to make. You always do all the possible pairwise comparisons. So you would you divide by all those possible combinations. Kind of a cute name, or I think it's a cute name, fun name. We're going to use the Bonferroni correction. Bonferroni. It kind of sounds like a cutesy swear word. Bonferroni. So if you're doing multiple comparisons, right, which is what we're doing. So the scenario of testing many pairs of groups is called multiple comparisons. The Bonferroni correction suggests that if you adjust your alpha level, so a more stringent significance level is more appropriate for these tests. So we use this adjusted alpha level where we take the original alpha, so 0.05, divided by K, capital K, where capital K is the number of comparisons being considered, where if there are lowercase k groups, then usually all possible pairs are compared, and K is going to be K times K minus 1 divided by 2. Tricky with the upper and lowercase k's, but there it is, right? So usually you consider all the possible groups. The reason I give you this formula, or I wanted to give you this formula, is because let's say you have 6 groups, right? And you're trying to list all the possible pairwise comparisons. It's helpful to know how many pairwise comparisons there are, right? And so, for example, if I let K be 6, right, then the number of comparisons is going to be 6 times 5 divided by 2, which is 15, right? So that means I have 15 pairwise comparisons. So I'm going to divide that 0.05, the original alpha level, by 15, because by the time I've run all those tests, right, then I'm going to have a total alpha level of 0.05, right? What does that make? What happens then? That means that it's going to be harder to reject H0, right? It's going to be harder to say that there are significant differences between these two groups, right? And that's a good thing. So, but what can happen is, dun, 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 dun. Sometimes we're going to reject H0 for the ANOVA, right? So we're going to find a significant ANOVA. And then once we do all our pairwise comparisons, it is possible that we don't find any significant differences because we've had to use this adjusted alpha level, right, is one of the ways. Okay. This doesn't mean that there is nothing going on, right? And the ANOVA was wrong. I mean, there's a chance that it was wrong, but usually it means that our sample sizes are too small, right? So we weren't able to pick up on differences that were that large. Yeah. I do want to just, I've got this kind of feeling that I said something after this. So let me just go to this morning. I did not. Aha. That is great news. memory serves. Quiz number 4, up to here. Another smiley face. Wow.
Except this isn't on the quiz.
No. Just me ticking some boxes. Yep, I said that. I said it and it was recorded and it's out there. All right, so what I want to do is I posted that those practice problems. So I want to go through and read those together and just pick up what type of question it is. Okay. And so as practice for the quiz, we will go through and identify the question types for some of these problems. So as practice for the quiz, we will go through and identify question types for the practice questions posted. All solutions will be posted, but I didn't want to post them in advance, kind of defeat the purpose. So we're not going to do all of these together. I will kind of let you go through them on your own. Okay. Hey, I guess I'm just consistent. I say the same thing over and over again. All right, so this first question I really like because there are a lot of different hypothesis testing questions that we could ask, okay? And so what I want to do is I'll read it to you because there's a lot, and then we'll talk about how each of these parts, right, make up a different type of question. Okay. And so coaching companies claim that their courses can raise the SAT scores of high school students. Of course, students who take the SAT without paying for coaching generally raise their scores too. A random sample of students who took the SAT twice found that 427 who were coached and 2,733 who were uncoached. Starting with their verbal scores on the first and second tries, we've compiled the summary statistics in the table below. So we've got the coached students, the uncoached students, their score, their mean and their standard deviations on try 1, their mean and the standard deviation of the scores on try 2, but also the gain, right? Try 2 minus try 1 makes the gain because presumably they are improving. Right, so that's why I did try 2 minus try 1. And then we have the mean and the standard deviation of the gains. Okay, so from here, there are lots of different questions that we could ask. Specifically, I've approached it from the standpoint of this coaching company. So what are some of the things that I could put out there and that makes me look good, right, as a coaching company? First one, kind of jumping into it here, did the students who were coached increase their scores significantly? Okay. So now, right, we're talking about, okay, just the coached students. Is there a difference between try 2 and try 1 or try 1 and try 2? However, we want to talk about it because these are matched pairs, right? So now this is paired data. So I want to analyze the gains, right? So here, paired data. I'm just going to write a quick summary because in the solutions I talk about why it's paired data. So just to kind of move through it a little bit quicker. But that's going to be paired data for the gain for the coached students. The second question, so that's something that I could put up for advertising, right? I significantly increased the scores of the students that I coached, right? That's good. Is there good evidence that coached students gained more on the average than uncoached students? That would be a selling feature as well, right? So now, all of a sudden, I'm comparing the coached and the uncoached students, which means I have two sample means, right? Two sample means of the gains, right? Kind of tricky, right? So in this case, this is a two sample means and of the gain, right? That I want to compare. If I can prove that, then that's a good thing as well, right? Do you want to gain significantly more than if you just study on your own? Right? That's a selling feature. What if someone says, oh yeah, but maybe your students were just scoring higher to begin with, right? Maybe they're just real keeners and they just score higher to begin with. Right. So then is there good evidence that there's a difference in scores on the first try for the coached and the uncoached students? Right? Which makes it a two sample means question again, but now I want to focus on just try one. Right? So you can see how all this information, we can construct lots of different types of questions from this one block of information. So it's a two sample means question, but for try one. That one's a doozy. I put it in the beginning on purpose, right? Because from here on out, we're kind of a little bit more on Easy Street. A little bit. Hey, Easy Street, there's our code in here. I know. But only so that you can see the mean and the standard deviations and the sample sizes of each of the groups. Right? And I did ask, so pipe operators are relatively new, but I think you guys are using pipes. Nice. That's snazzy. I guess they were new like 3 years ago. But someone sent me a question and they're like, here's what I've done so far with these pipe operators. And I'm like, oof, it was my niece actually. And she was doing a stats course and she's like, I don't know what to do here. I'm like, what are these things? Oh, cool. And they were like pretty brand spanking new at the time. So I am gonna just grab this. But because we're not answering the question, I'm going to make it quite small. Put it on one page, maybe. Might be nicer of me. Okay. You know what? Because these are going to be just slightly different. Of course. Sneaky, sneaky. Okay. Chicken farming. And this is the one that I posted that RMD file for, just so you can see kind of how you would do that analysis. Chicken farming is a multi-billion-dollar industry, and any methods that increase the growth rate of young chicks can reduce consumer costs while increasing company profits, possibly by millions of dollars. Cruel world. An experiment was conducted to measure and compare the effectiveness of various feed supplements on the growth rate of chickens. Newly hatched chicks were randomly allocated into 6 groups, and each group was given a different feed supplement. Below are some summary statistics from this data set. So, and I couldn't figure, I think it's casein? I don't know how to say it. I know how to say horse bean though. Horse bean, linseed, meat meal, soybean, sunflower. Those are the different feed options that they were given. And the chicks, kind of between 10 and 14 chicks were allocated into each group. Probably a sad backstory why there's only 10 in the horse bean group, but that's not for me to say. All right. So already, when I see multiple groups, more than 2 groups, here I have 6 groups, right? I have the mean, I have the standard deviation. As soon as I see that, my gut goes ANOVA, right? But we'll kind of slow it down a little bit, because first we want to know, do these data provide strong evidence that the average weights of chickens that were fed linseed and horse bean are different? That's only 2 of these groups, right? Making this a 2 sample means question. Right, because I just want to know about the 2 groups. How do these 2 groups compare? Ignore everything else. That is a question that we could ask, fine. But then, of course, the follow-up is conduct a hypothesis test to determine if these data provide convincing evidence that the average weight of chicks varies across some or all groups, right? And so that's going to be the ANOVA, right? Because I'm comparing more than 2 groups. All right. Good. And like I keep saying, as soon as you've decided what type of question you have, that determines where you are on your formula sheet, right? And it determines kind of what values you need to look at, right? Thinking specifically for that coaching question, right? If you're analyzing the 2 gains between the 2 groups, you can ignore the rest of the information, right? And so kind of narrows it down. How about this one? As part of the study on tipping in a restaurant, I feel like there's punctuation missing, but in a restaurant, psychologists studied the size of the tip in a restaurant when a message indicating that the next day's weather would be bad was written on the bill. I know there's a follow-up part to this where, okay, now if we write that the message is going to be that the weather's good, right? And you can compare the 2, right? So you can see how there's different questions that we could build up from all these. The mean tip from 20 patrons was 18.19% with a standard deviation of 2.1%, measured in percent of the total bill. Do the data give convincing evidence that the mean percentage tip for all patrons of this restaurant, when their bill contains a message that the next day's weather will be bad, is less than 20%? And then I thought this was a bit rich because I stole this in like 2015, making it even worse. 20% is an often recommended size for restaurant tips. To be fair, though, it is from the States, so, or the textbook I stole it from was from the States. Still, 20, come on. 2015, no way. 18 was like pretty generous, and back then, I don't know. All right, so, and can you imagine getting a bill? Oh, sorry, weather is gonna be so bad tomorrow. It's gonna rain. What? Thanks for dining with us. Okay. What type of question is this? Got a one sample means question, right? Because I only have one sample of 20 patrons. I have the mean and the standard deviation of that sample, right? And I want to compare it to 20%. So this is a one sample mean question. For the one sample mean, that's the only one where we have that added difficulty of figuring out what mu naught is going to be. So what's my null hypothesis about? So for the one sample means questions, I do want to talk about the null hypothesis. So here mu is equal to 20%, right, or 20, right? Because I want to compare my sample mean to 20%. And our alternative in this case, if I want to know if the mean is less than 20%, then that's going to be reflected here. Mu is less than 20. I typically say that you should convert percentages to proportions, and you absolutely can. You'll find the same results. But then I felt like that got a little confusing because it's not a proportion question. So that's why I'm keeping just the 20, and you can keep the 18.19 and 2.10. But whatever you do, if you do convert them to proportions, convert all of them to proportions. Right, so if you're going to do 0.2, you should do 0.1819, 0.021, right? Be consistent. Okay, but you're fine to just keep the value. Good. How about another one? The placebo effect is particularly strong in patients with Parkinson's disease. To understand the workings of the placebo effect, scientists measure activity at a key point in the brain when patients receive a placebo that they think is an active drug, which is a placebo, and also when no treatment is given. The same 6 patients, which immediately I start to think paired data. So now I'm just going to follow up, right? If I'm talking about the same 6 patients did something, right? That's an alarm bell that this is going to be paired data. So let's just confirm. Are measured both with and without the placebo, right? At different times. The 6 differences, and this really seals the deal here, the treatment minus the control had a mean and a standard deviation of blah. Doesn't matter. Right? But this is the mean of the differences and the standard deviation of the differences. Right? Is there significant evidence of a difference between treatment and control? So a difference from 0. So this is going to be paired data. Okay. How about this one? A clinic in rural, I can never say rural, Guatemala measures the blood calcium level of 160 healthy pregnant women at their first visit for prenatal care. They find the mean is 9.57 and the standard deviation is 0.4. Is this an indication that the mean calcium level in the population from which these women come from differs, I added the from, differs from 9.5? Carry out the hypothesis test and then construct a confidence interval and you'll have those solutions. But for now, right, this is just a one sample mean question. Why? I only have one sample of 160 pregnant women, and I have the mean and I have the standard deviation of that. And I want to compare that sample mean to 9.5, which means that my null hypothesis is that mu is equal to 9.5, right? Because I want to compare 9.57. Is it, does it differ from 9.5, which means my alternative hypothesis is that mu is not equal to 9.5. Just do two more, and then I'll leave the rest for you guys to work through. Let you fly on your own. A trucking company would like to compare two different routes for efficiency. I was going to say efficacy, no, efficiency. So right away, two different routes. I feel like this is going to be a two sample means problem, two independent sample means, but I definitely have two samples, so it could be paired. Let's just read up and confirm. Truckers are randomly assigned to two different routes. You're going to go this route, you're going to go this route. So 20 truckers follow route A. Following route A, report an average of blah and a standard deviation of blah. So that's sample one. 20 truckers following route B report an average of 43 and a standard deviation of 2 minutes. Right? And so now I have these two independent samples. So sometimes I like to throw in that independent, right? Just to emphasize that, okay, these are two independent groups. There's no pairing going on. We want to find the 95% confidence interval, and then will the company save time? I'll let you do that on your own. But here, this is two, and I'll throw in independent sample means, right? I want to compare route A with route B. And then the last one is probably my favorite question. Not ever, but I don't know. It's up there. I just think it's so cute. And I did check it one time, and I did find something along these lines, and I'm sure there's a quote, but fancy pets are big business. So a young entrepreneur, age 12, decided to breed golden hamsters, a type well known to pet stores and collectors of hamsters. Can you imagine? Oddly enough, so here's the piece that I find interesting. Oddly enough, nearly all golden hamsters in captivity are descendants of one litter found in Syria in 1930. That's crazy. So that I had to follow up on, and I should have a footnote somewhere, but maybe I suppressed it. Of 47 recent litters, obviously this part is made up. The entrepreneur at age 12 breeding hamsters, her parents must be so proud. Of 47 recent litters of hamsters, yikes, there were an average of 7.27 baby hamsters with a standard deviation of 2.5 hamsters per litter. Yikes. We're going to find and interpret a 90% confidence interval. So without reading part B, I guess it kind of gives it away, but this is a one sample means question, right? I have one sample of 47 recent litters. I have the mean and I have the standard deviation. I have nothing to compare that mean to yet, right? So this is a one sample mean question until I read part B. Teddy hamsters, which is another breed of hamsters. We had a teddy hamster and we named him Teddy. But hindsight, there was probably room for improvement, but teddy hamsters have an average of 5 baby hamsters per litter. Is there evidence that golden hamsters have significantly larger litters than teddy hamsters? So now, golden hamsters, I had a sample average of 7.27. Is that significantly larger than 5, right? That's what I want to know. 5 representing the teddy hamsters. So my null hypothesis here is going to be that mu is equal to 5. 7.27 is not significantly different from 5, but what we're hoping to show is that mu is greater than 5. Yeah. So work through the remaining questions on your own for practice. Oops. So many smiley faces today, and they're all kind of smirking. So I think there's 8, 9, 10, 11, 12. That's it. So I'll show them on here in case you wanted to do it here, but I know you guys have a lot going on. So I'll stop the recording. Are there any questions before I do? No. All right. Then I'm going to stop the recording